Hello, everybody. This is Physics Lab 2. My name is Edwin Torres, and I'll be showing y'all exactly what I did today. So basically, I put me and my classmate recorded this video, and we imported it to Tracker, and so I used the a quarter for this experiment. The and I we threw it across the table. The motion stayed in 2D plane, and my camera stayed still while I was recording. I used a calibration stick and tracker so the program could convert pixels into meters. The mass of the quarter is 0.00567 kgs. The object was released around 68 frames. So right here is a 68, and the tracker gave me an X and Y position of each frame. In Tracker, I created a point mass track and click the center of the coin frame by frame. Tracker output a data. So as you can see here, this is the data, what it gave me after I tracked it frame by frame. And so here is the coin flip, and that's the data. And I exported it to Google Sheets, my data. So this is the experimental data right here. As y'all can see, this is all the numbers I got. And and then next I made my glow script model using only gravity. That means the net force is F net equals F gravity equals 0, negative mg, and 0. So the acceleration is constant. And let me show y'all this. It's constant downwards at g equals 9.8 ms squared. I set the initial position velocity using the first two tracker rows, and I ran simulation for about 0.47 seconds to match the real video time. The gravity only model gives a smooth parabola, but it does not perfectly match the experimental motion. Um, so this is the curve. Boom. It's really nice. Then I made a second model that includes drag. The drag force points opposite the velocity has magnitude and proportional to speed squared. F drag equals negative V times V squared times V hat. So the total force become F net equals F gravity plus F drag. I adjusted the drag constant to fit closer um to fit closer see the gravity only, the experimental one, the one that I did with my classmates. So this is the calculations and everything that came with no drag. And for Model 2, we did gravity plus quadratic drag. As y'all can see right here. I adjusted the drag constant B until simulated trajectory fit closer to the experimental data. The B value I used was B equals 0.0008. This was my final drag, or say the final B. With drag included, the simulated curve become closer to the experimental trajectory compared to the gravity only. So this is all three. Right here is all three of my things. And as you can see, the gravity and the drag are pretty similar in the curve. And when I compare all three of the same chart, the experimental data is real motion from tracker. The gravity only mode model is close, but it starts drift away from the real data. The gravity plus drag model matches better because drag reduces the motion over time, especially speed increases. So overall, the drag model is more realistic. So key inputs, these are the things I put in the Python close script. So, uh, in a short toss, the object usually doesn't fall enough to reach terminal velocity. A better test, drop the quarter or later object from a taller height and track VT. What if throw straight up from the initial speed? Time to return to the ground would be longer because of all V. Zero is vertical. So, in conclusion, um, my lab report, I tracked it on the motion and tracker, built two glow script models and compared trajectories. The model, including drag, matched the experimental data better. Thanks for watching.